Hello. Today in this video I will give you an introduction to waves. Many of you have put a stone in a pond and watched the ripples generated, right? We call it as waves in physics. Then what is a wave? Can you define it? Wave is a form of disturbance, or we say it is a transfer of energy. And how is the energy transferred? Obviously, there is no transfer of particles of the medium from one end to another. How can you say that? There is no transfer of particles. How can you prove it? Drop a paper ball on the water surface. You can see that the paper ball simply vibrates up and down. That means the molecules of water are not propagating outwards. It's just the propagation of energy in the outward direction when you put a stone in it. And that gives you the definition of a wave. A wave is just a disturbance, propagation of disturbance, and the propagation is due to the repeated periodic vibration of the particles of the medium about their mean position, and the motion is handed over from one particle to the other without the motion of the medium itself. Another example of a wave is a sound wave. When a source of sound vibrates, it transfers its energy to the surrounding particles. Those particles then bump into the next ones and so on. That is, in a stereo speaker, you have a diaphragm which will be vibrating. It moves back and forth. When the diaphragm moves to the right, the air on that side gets compressed, which results in compression. At the same time, there is more space for the molecules on the left. That side there will be rarefaction. So the sound wave propagates as a mix of compressions and rarefactions. If in this case also there is no transfer of molecules. If there was transfer of molecules, we call it as a wind. It's not a sound wave. If you consider the case of ripples in a pond, there the particles vibrate about the mean position in a direction perpendicular to the direction of propagation. Such waves are called transverse waves. When a transverse wave propagates through a medium, if we plot the vibration of particle with respect to the time, in this figure, the maximum displacement in the positive direction is called crest, and the maximum displacement in the other direction is called trough. The distance between two consecutive crests or two consecutive troughs is defined as the wavelength. In other words, the wavelength can be defined as the distance travelled by the wave during the time a particle of the medium completes one vibration about its mean position. However, if we are plotting this amplitude versus time, the distance between these two will give you the period. That is, the period of a wave is defined as the time for a particle on a medium to make one complete vibrational cycle. And the number of waves that pass a fixed point in 1 second is defined as the frequency of the wave. In 1 second, there will be new vibrations in 1 second, and if higher the number of wave cycles, greater will be the frequency, as you can see in the figure, low frequency to high frequency. So the number of waves that pass a fixed point in 1 second, that is referred to as the frequency of the wave. New vibrations are possible in 1 second, and the time taken for one vibration, that is defined as the period t. So nu is equal to 1 over t. And the distance travelled in one complete vibration, that is the wavelength lambda. Distance travelled in 1 second, since there are new vibrations in 1 second, the distance travelled in 1 second will be equal to nu into lambda. And we say the distance travelled in 1 second is the velocity. So the velocity of the wave is v equal to nu into lambda, where nu equal to 1 over t, where t is the period of the wave. It should be noted that the waves that we discussed, such as water waves and sound waves, they require a material medium for its propagation. Such waves are called mechanical waves or elastic waves. And the medium also requires the property of elasticity, since the particle must regain its original position for wave propagation. However, there is another category of waves which do not require a material medium for its propagation. Examples are electromagnetic waves, radio waves, X-rays, light rays, etc. are examples for electromagnetic waves. They are called non-mechanical waves or non-elastic waves because they do not require a material medium for their propagation. And if you remember, the water waves, they are transverse waves. Similarly, electromagnetic waves are also examples for transverse waves, whereas sound waves are examples for longitudinal waves, where the particles of the medium vibrate parallel to the direction of propagation. In the next video, I will discuss about progressive waves. Thank you. Hello. In the last video, I have given an introduction to waves, and in this video, let us see how we can represent a wave mathematically. Consider a person is, let's say a person is jerking a rope which is tied at one end. What will happen if he is jerking once? A wave pulse will start propagating from left to right. Can we represent it mathematically? If the displacement we want to represent, let's represent it as y is equal to f of x. Then what is f of x? It gives you the shape of the wave, or in other words, it gives us the displacement of different points along the wave propagation direction from their equilibrium positions. The shape of the wave will change with x and t in general. But suppose for the time being, let's say there is no change in shape of the wave. Then one can say that if f of x is the shape of the wave at time t equal to 0, and if the wave is propagating with a velocity v from left to right, then the displacement at a distance x plus vt will be the same, at time t will be the same that at x at time t equal to 0. A more general form of wave pulse propagating from left to right is usually represented as f of x minus vt, and for a wave pulse or for a wave propagating from right to left is usually represented as f of x plus vt. So a general equation of a wave propagating along x-axis is usually written as a combination of a function of x or x minus vt and another function of x plus vt. Let's see what's the differential equation of a wave. The equation of wave motion, as we told, for a wave pulse propagating from left to right, the general form is y equal to f of x minus vt. Then differentiate both sides with respect to x twice. What will we get? Dou y by dou x is f prime of x minus vt, and dou square y by dou x square will be f double prime of x minus vt. Now differentiate the equation 1 with respect to time. We will get dou y by dou t, which is equal to, we have the function, we have f of x minus vt. So when you differentiate with respect to t, we will get minus v into f prime of x minus vt. And when you differentiate it once more, we will get dou square y by dou t square equal to v square into f double prime of x minus vt. And from equation 3, we have f double prime of x minus vt is dou square y by dou x square. So substitute 3 in 5. Instead of f double prime of x minus vt in equation 5, we can give dou square y by dou x square. And we will get dou square y by dou t square equal to v square into dou square y by dou x square. Or we can say dou square y by dou x square is equal to 1 over v square into dou square y by dou t square. So this gives us the one-dimensional differential equation of wave motion. Okay, let's check once more. The equation 2, we have dou y by dou x, and equation 4, we have dou y by dou t. We have on the right side f prime of x minus vt. So let's compare these two equations once more. We can see that dou y by dou t equal to minus v into dou y by dou x. What is dou y by dou t? It represents the displacement with respect to time. In other words, it's a particle velocity. And we have this particle velocity is equal to minus v. V is the wave velocity into dou y by dou x. Dou y by dou x is the slope of the y-x curve. Kindly note that even if the equation dou square y by dou x square equal to 1 over v square into dou square y by dou t square is satisfied by a function, it may not be representing a wave always. The condition is that the values must be finite for all x and t. So all functions satisfying the second order wave equation cannot represent a wave motion. Besides satisfying the differential equation, the function must be finite for all values of x and t. Let us see two functions. We have two functions. One is y equal to x plus bt and the other function is y equal to a sine of kx minus omega t. Let us see the functions one by one, whether both satisfies the wave equation, whether both satisfies the differential equation. Then we will check the finiteness and then we will conclude whether that function can be used for representing a wave or whether the function represents a wave. Let's take the first case, that is y equal to x plus bt. We should find dou square y by dou x square and also we should find dou square y by dou t square. So for that, let's first find dou y by dou x. Y equal to x plus bt. So dou y by dou x is a. And dou square y by dou x square is 0 since a is a constant. And again, we have to differentiate with y with respect to time. So that will give us dou y by dou t is b and dou square y by dou t square is equal to 0 again because b is a constant. You can see that the equation, the function satisfies the wave equation, right? But the problem here is we doesn't have any finite value for x and t. For all values of x and t we must have finite values. In this case, both values are 0, even though dou square y by dou x square is equal to 1 over v square into dou square y by dou t square. Both sides are equal to 0. We doesn't have any finite values. So this function cannot represent a wave. Let's take the other example, y equal to a sine of kx minus omega t. We can find dou y by dou x, that is equal to a cos of kx minus omega t into the derivative of kx. That will give us ak cos of kx minus omega t. Again, dou square y by dou x square, we can see that it is minus k square into a sine of kx minus omega t, and a sine of kx minus omega t is y. So we have dou square y by dou x square equal to minus k square y. Similarly, we can find dou square y by dou t square, which is equal to minus omega square y. Comparing the equations, we can see dou square y by dou t square is equal to minus omega square y, and again dou square y by dou x square equal to minus k square y. We can find y from both sides and equate. You can see that dou square y by dou t square equal to omega square by k square into dou square y by dou x square. So this is of the form of the wave equation where we have for k square we have omega square by k square. Till now we were discussing about wave pulse. That is, in the first example we consider a man who is jerking a rock once. And we have a wave pulse propagating from left to right. We represent it by f of x minus v. Suppose if the man is jerking continuously up and down, what is the net result? The up and down motion of the rock continuously will generate a continuous wave. And if that wave is propagating through a medium continuously, if such a wave, such a periodic wave is propagating through a medium continuously, what we call it as a progressive wave. So we can define a progressive wave as a wave which travels continuously in a medium in the same direction without any change in its amplitude. Such a traveling wave is called a progressive wave, a wave which travels continuously in a medium in the same direction without any change in its amplitude. Usually, such periodic waves are represented by harmonic functions like sine function or cosine functions. So, this is one form where we can represent a progressive wave y equal to a sine of 2 pi by lambda into x minus vt plus phi 0. Phi 0 is the initial phase of the wave. And 2 pi by lambda equal to k is called the wave vector or the propagation constant. And we can write this 2 pi by lambda into v, that will give you v by lambda is nu, that is frequency. So that is 2 pi nu, that will be equal to omega. So we have the different equations, v equal to nu lambda, 2 pi by lambda equal to k. You can use all these equations to find out the different ways in which you can represent the same equation. Okay, let's do that. Instead of the first equation, you can take 2 pi by lambda inside. You can see that will give you y equal to a sine of 2 pi by lambda into x minus 2 pi by lambda into dt plus phi 0. This is equal to, what is 2 pi by lambda? We say that is equal to k, that is the wave vector or the propagation constant. So you can write this as kx. Then 2 pi by lambda is 2 pi by lambda into v can be represented as omega, as we say. So that the equation is actually y equal to a sine of kx minus omega t plus phi 0. We can actually start from this equation and form the other equation also. That is, start from y equal to a sine of kx minus omega t plus phi 0. We have noticed that y equal to a sine of kx minus omega t is an equation of a wave. It has finite values for dou square y by dou t square and dou square y by dou x square, and it obeys the wave equation. So adding an initial phase to it, we have y equal to a sine of kx minus omega t plus phi 0. K is 2 pi by lambda. Again, omega is 2 pi nu and v equal to nu lambda. Use those equations, you will get equation 1. So equation 1 and 2 represents two different equations, two equations of a wave. And again, you can actually rearrange and you can see that this is, it can be written as 2 pi by lambda. If the lambda is taken inside, we'll get 2 pi into x by lambda minus v by lambda into t plus phi 0. Or v by lambda is again nu. So this is another way, equation 3 is also another way of writing a wave. And again, we have nu equal to 1 over t. So again, you can rearrange this 1 by lambda can be written as, or you can actually multiply and divide by nu, the numerator and denominator, and you can rearrange this equation based on nu lambda, v equal to nu lambda, and 1 over t can be written as nu. You can see that the same equation can be written as y equal to a sine 2 pi nu into x by v minus t plus phi 0. So these are all different equations, or we can write actually this 2 pi nu as omega, or this is another way of writing the equation y equal to a sine of omega into x by v minus t plus phi 0. These are this equation 1, 2, 3, 1, 2, 3 and 4 are all different forms of a plane progressive wave. Let's do an example. Suppose you are given a progressive harmonic wave in a string as y equal to 5 sine 2 pi into x by 100 minus t by 0.02 with length expressed in centimeter and time in second. The question is to find the wavelength, amplitude, frequency and velocity of the wave. So you are given y, compare it with the standard equation. We have y equal to a sine 2 pi into x by lambda minus t by t. Comparing, we have the amplitude a equal to 5 centimeter. Lambda is 100 centimeter, or that's 1 meter. Then time period t is 0.02 seconds and frequency is mu equal to 1 over t. You get it directly, that's 50 hertz. Then wave velocity v is related to nu and lambda, v equal to nu lambda, which will give you the wave velocity. So if you are given a plane progressive wave of this form, you can actually determine everything related to wave like amplitude, wavelength, time period, frequency, wave velocity and so on. This is another example. You are given a plane progressive wave y equal to 10 sine of 0.1x minus 4t. Y is expressed in centimeter and time t in second. Calculate the amplitude, frequency, velocity and wavelength of the wave. Also find the maximum transverse speed and acceleration of a particle in the string. So you compare this equation with y equal to a sine of kx minus omega t will give you a, k and as well as omega. And we have k is equal to 2 pi by lambda will give you lambda, and omega is 2 pi nu, that will give you the frequency. And we have v is equal to nu lambda, which will give you the wave velocity. And how can you determine the maximum velocity as well as the acceleration? You have the equation for y is equal to a sine cos kx minus omega t of that form. Differentiate it, we'll get dy by dt, that will give you the velocity. And the maximum velocity, how can you determine the maximum velocity? The maximum value of the cosine function is 1. So if the cosine function goes to 1, dy by dt will become minus 40, or this 40 centimeter per second, or it is 0.4 meter per second. Similarly, you can find the acceleration by finding tau square y by dot t square, and the sine function also, the maximum value will be 1, so that will give the maximum value of the acceleration as 1.6 meter per second square. In the next video, we will discuss about the energy of plane progressive waves.